we present our work approximating continuous convolutions for deep network compression. In general, discrete n-dimensional convolution can be expressed in the form presented. By considering the tensors x and w as piecewise functions over space, we can rewrite this expression in a continuous form. This continuous form allows us to replace the tensor w with a function that represents the same values. If we are then able to choose a function that can encode the essential characteristics of w with fewer parameters, we can reduce the memory footprint of the network. As functional approximation has been studied for over a century, there is a significant body of work to draw inspiration from. From this body of work, we use two common functional series to approximate w, specifically the cosine and Chebyshev series. Provided specific conditions are met, and given the redundancy often found in deep networks, these series are well able to approximate the filters found in deep networks. By using fewer coefficients in the series than the number of weights in the tensor w, we are able to reduce the memory needed to store the filter. Further details of the motivation driving our choice of approximating functions is presented in the paper. Because we choose a smaller number of coefficients for the approximation than there are values in the tensor, we are not able to use a closed-form solution to find an initial approximation. Instead, we use simple iterative gradient descent, minimizing the L2 error between the original filter and the approximation. Normally, in numerical approximation with Chebyshev series, care has to be taken to avoid Runge's phenomenon, where approximation error at the ends of the interval increase with the number of coefficients. However, because we only ever evaluate the approximation at the sample locations, we can safely ignore this potential issue. After finding the initial weights, we then fine-tune our approximations for 5 epochs on the relevant dataset. To summarize and clarify what we've presented so far, we now give a simple overview of the whole method. Starting with the discrete weights of an individual filter from a layer in the network, we then treat this tensor as a continuous function over space. We then approximate this function using either cosine or Chebyshev series. Compression is achieved by using fewer coefficients than values in the original filter kernel. We then save these coefficients rather than the original filter. At inference time, the filter is reconstructed from the stored coefficients. Unlike comparable methods, our approach does not require training from scratch. Instead, we require only a small amount of fine-tuning after the initial approximation. This table shows the results of applying our method to the CIFAR-10 dataset using the ResNet 20 and 32 architectures. These models consist of 4 blocks of layers, with varying numbers of channels for each block. The numbers in the layer column represent the number of coefficients per filter used in each block. The pre-top 1 columns show the accuracy immediately following the initial approximation, and the post-top 1 after fine-tuning. Our method is able to reduce the size of ResNet 20 by 42%, with only a 1% reduction in accuracy. Whilst not designed to approximate previously learnt filters, we applied our regression and retraining approach to the comparable methods fractional filters and FRAC-SRF. We found that fractional filters was not able to approximate the kernels to any meaningful degree, even after fine-tuning, achieving no better than random guessing, that is to say 10%. FRAC-SRF was not able to approximate the kernels initially, but was able to recover some accuracy after fine-tuning. We conduct further experiments on the ImageNet dataset. Like ResNet 20 and 32, the structure of ResNet 18 means that compressing the final block of layers has outsized performance on parameter count. Although the first configuration reduces the number of parameters in the first layer by 30% with no loss in top 1 accuracy, the distribution of parameters in the network mean this has barely noticeable effect on the overall parameter count. Here we see that our method is able to compress the layers of ResNet 18 by 50% whilst losing only 1.86% accuracy. To better investigate the capability of our network on larger kernels, we apply our method to the depth-wise 7x7 layers found in ConvNext. Our method is able to compress these layers by 42% with only a 2.8% loss in top 1 accuracy. We suspect that the impact of our method is not as strong as on ResNet 18 because of the significantly more discontinuous kernels found in the ConvNext model. Here we show filters from the layers of both ResNet and ConvNext. The top row is the original 7x7 filter. The next 2 rows then show 5th order cosine series and Chebyshev series approximations of the original filter. Finally, to show that our method can complement other existing methods for reducing model size, we apply our method alongside quantization. We use a basic quantization scheme and apply it to the coefficients of our series approximations, as well as the network activations. Our results show quantization can be applied alongside our method with only minor accuracy loss. Further information on quantization is presented in the paper. Thanks for listening. To check out our project page, scan the QR code on screen.